Today we'll start with the encryption algorithms. Now, encryption algorithms are a very fundamental block of any blockchain system. So, when we are talking about a blockchain, now a blockchain is called a blockchain because it is formed by chaining of blocks, and this chaining of blocks is what gives blockchain the name blockchain. So, when we talk about chaining in a blockchain or chaining in any kind of distributed ledger, the technology or the algorithms that are used for chaining are these encryption algorithms. So in blockchain, we make use of SHA-256, which is the secure hashing algorithms, which is used for linking the blocks in the blockchain. And this is what provides the immutable property to the blockchain. We'll shortly see how immutable property is provided by hashing. Then whenever we put some information inside the blockchain, it is never in plain text. That is, the information that is put inside the blockchain is not something that is readable to you and me. The information is always encrypted in nature, and we have several encryption algorithms which are used. Now, one of the reasons for using encryption is that it helps us in optimization of space. That is, we are able to store more things in a lesser amount of space. Also, the information is protected in nature. So encryption is used in blockchain. So we use hashing algorithms, we use some encryption techniques, and finally we make use of some digital signatures in blockchain. So suppose I am a user, I want to transfer some amount of money to some other person. Suppose I'm on the Bitcoin blockchain. So I have to create a transaction in order to transfer any amount of Bitcoins to any other person. So whenever you download the Bitcoin software, you are provided with a public key. That is, you have one public address, and using that public address, you derive your private address. So that private address serves as your digital signature. So suppose I send something on the internet, the Bitcoin network. So since there is no intermediary, all the transactions are facilitated by the peers on that Bitcoin network. So we need to ensure that whenever some transaction is generated or some transaction is submitted to the transaction pool, so there must be some kind of mechanism which will ensure that, okay, if the transaction says that A has sent money to B, we are able to verify that, okay, A has sent money. So we need to verify the identity of the person. So for that, we make use of digital signatures. So with respect to any blockchain, there are these three concepts that we use. One is the hashing techniques. Then we make use of some digital signatures. And finally, some algorithms for encrypting our data. So we'll see all of these three uh, encryption techniques shortly. So when we talk about our computer system, we use our computer system to communicate with different users. Suppose you have a friend and you are chatting with her on the internet. So the data that you generate, it travels from your computer, makes use of the communication channel, and it gets transmitted over the network. So the computer data often travels from one computer to another, and when it does so, it is no longer protected by your physical system. That is, your physical system does not take the responsibility of protecting that data that has already been sent on the network. Now, once the data is out of your physical surroundings, there may be people like uh, hackers or somebody like cyber attackers who may try to forge your data or try to modify the data, that anything like they could have any bad intention, either they do for their like their own benefit or some amusement. So there is a possibility that your data can be forged or modified. So we make use of cryptography in order to make our data safer when it is in transmission. So what cryptography does is it reformats our data, transforms our data, and makes it safer when it is in transmission, that is, when it leaves the physical system. And cryptography, the technology is based on some secret codes, and it also makes use of some modern mathematics that protects our data in powerful ways. So now, modern encryption technologies, modern cryptography makes use of some complex mathematical formulas, which are known as encryption algorithms, which are used to protect our data. Now, why do we need encryption? So there are several reasons for needing encryption. First is privacy. Now, what encryption does is it guarantees that no one can read our message or access our message unless they are the legitimate recipient or the data owner. So, when we are encrypting our data, it will prevent cyber criminals, hackers, internet service providers, spammers, or in some cases, even government institutions from accessing and reading your personal data. And it helps protect your data, your information from data breaches, whether the data is at rest or the data is in transition. Also, it helps to authenticate the user that, okay, you are who you claim to be. So you can trace back to the owner of that data, and it helps in authenticating the data as well as authenticating that, okay, this is the user who has created and sent the data. So even there are some kind of public encryption systems. So whenever you are using a website, so the website's server will have some kind of encryption techniques which will like help you identify that, okay, this is a legitimate website. It will help establishing the credibility of the. So encryption helps us in a large number of ways. So now instead of using some like simple addition and subtraction, like you can encrypt your information in a lot of ways. But in modern encryption, what we do is we make use of some mathematical formulas, some complex mathematical computations. And the reason for doing so is that because now the hackers have computers that are capable of performing far more complicated calculation in a shorter amount of time. So we need to make the encryption also more complex so that our data is not exposed but remains encrypted. Also, if encryption is not randomized enough, a computer program will be able to decrypt it. So what happens in cryptography is that your data, your plain text is scrambled in such a way that it is beyond human recognition. So let us now see some of the basic terminologies which is associated with encryption. So We have a plain text. Now, plain text is the original message. Then we have the ciphertext. Now, ciphertext is the coded message. Cipher is the encryption algorithm which is used for transforming the plain text into ciphertext. Then we make use of a key, which is the information or a string of characters which is used for converting our plain text into ciphertext, and it is only known to either the sender or the receiver of the message. Then we have encryption, that is, we are enciphering, converting the plain text into ciphertext. Then we have decipher, which is decryption, which means we are converting the ciphertext from the plain text. And then we finally know what cryptography is. It is the study of the encryption algorithms, encryption techniques. And then we have a term which is called cryptanalysis. Cryptanalysis is code breaking. Now, whenever some programmers or people who develop these encryption algorithms, what they have to do is they have to perform some kind of crypt analysis on their algorithm. Now, the reason for doing crypt analysis is to ensure that if our algorithm is exposed to attackers, to hackers, the hacker would not be able to decipher the ciphertext without having the key. So cryptanalysis ensures how strong your or weak your algorithm is. So it is a mechanism which will ensure that your ciphertext cannot be converted into plain text without having the key. And cryptology is the field of studying the cryptography and cryptanalysis. Now, let us see this with the help of an example. So, suppose this is your plain text. It will have some message written onto it. Now, we pass this plain text through some kind of encryption algorithm. Now, in this encryption algorithm, we will also pass a secret key. So what we now receive is the ciphertext. Now this ciphertext is transmitted over the network. Now all of this is happening at the sender side. This ciphertext has been transmitted over the network. Now here at the receiver's end, we will have a decryption algorithm. This decryption algorithm, what it will do is this decryption algorithm along with the secret key will convert this ciphertext into the plain text. Now this decryption algorithm, it is reverse of encryption. And this is the steps taken on the receiver side. So we have a plain text, which is the message. Suppose we have a user whose name is Alice. And here we have another user whose name is Bob. So we are saying that Alice wants to send a message to Bob. So what she'll do is she'll write the message. Now this message is in plain text. This message is the input. Now this input goes to the encryption algorithm. Now plain text is any readable data. That is, you can make sense of what is written. You type a message, you send a message to your friend, you can read that message that is intelligible to you. So again, here we have a message which is in plain text. It is the input. This input is passed through the encryption algorithm. Now, this encryption algorithm, what it will do is it will convert the plain text into ciphertext. Now, this ciphertext is also called as encrypted text, which is a series of like randomized letters and numbers which the humans can't recognize. They can't make sense of it. So again, here we can see we are making use of a key, which we are calling the secret key. Now, the key is a string of characters which is used within an encryption algorithm for altering the data so that it appears random. And encryption algorithm takes the plain text, runs that through the algorithm, that it runs the message through the algorithm, and it produces a ciphertext. So here we have a plain text, which is the input. We have an encryption algorithm. So we run the encryption algorithm on the plain text, which produces a ciphertext. Ciphertext is also called the encrypted text. We make use of a secret key, which is like a string of characters, which is used along with encryption so that it can alter our input text and make it random, so that our text appears random. Now this ciphertext or the encrypted text is transmitted over the network because we are sending a message from Alice to Bob. So this ciphertext has to be transmitted over the network. So here what we see, this is the sender's side encryption. Now the ciphertext is transmitted over the network on the receiver's side, that is on Bob's side. We have a decryption algorithm. Now this decryption algorithm is reverse of encryption. Now Alice and Bob both share the secret key. So secret key and this ciphertext or the encrypted text is passed through this decryption algorithm to get the plain text. So this decryption happens on the receiver side. So here we can see is that when we are passing a message on the network, that is Alice is sending a message to Bob and she's making use of the communication network, the message is not exposed. The message is encrypted and that encrypted message is sent to Bob. So this is the basic of what encryption is. Now, we have already seen this terminology associated with encryption and encryption algorithms. Now, let us see what ciphers do. So, ciphers help us in providing confidentiality. Now, suppose when we're talking about Alice sending a message to Bob, there is a intruder, and this intruder is Eve, who wants to listen to the message. She wants to know the message that Alice sent to Bob. So suppose the message is M, the message was encrypted, so this message now becomes C. So Alice encrypts the message M, and she transmits this message to Bob. Now, can Eve do anything? She cannot eavesdrop upon the message because this message is already encrypted. So Eve can't see what Alice and Bob are saying. Now, let us see a scenario where Eve can eavesdrop upon the message. Now, let us see what will happen if Eve could intercept the message that Alice sent to Bob. So we take here a scenario where Eve can get between Alice and Bob. And what if Eve can manipulate the data? So Eve decides that she'll send a message to Bob, and the message is M. But now what's happening is Eve is intercepting the data. So instead of the message M going directly to Bob, there is a mediator here who is diverting the message M to her. Now Eve is diverting that message M that Alice wants to send to Bob. She's diverting that message to herself. And what she does is she decides that she'll make a few changes to the message. So what Eve does is she replaces the message M with M dash. So the original message was M, and originally the message was meant to be sent directly to Bob. But since she is eavesdropping on the network and she wants to tamper with the data, what she does is she decides, okay, now I'll change the message. So suppose it was, if it was some very high security information, that is, this was some information that had to be protected, and Eve manages to replace that information, then there could be a loss of data, a loss of information, and in some cases, if it was some financial information, there could be a loss of money. So Alice initially wanted to send the message to Bob, but Eve intercepts that message and decides that she'll make a few changes for herself. So she replaces the message M with M dash. And then she sends this M dash to Bob. Now, Bob, thinking that this message has been transmitted or sent by Alice, will think that, okay, this message was meant to be M dash. He would not know that this message was initially M, but there was an eavesdropper on the network who changed the message M to M dash. Now, the question here is, the message M had to be sent directly to Bob, but Eve made the changes and the message M became M dash. Now, how can Bob tell if Alice's message was modified? So let us see how the receiver would be able to tell if the message that has been received from the sender is modified or not. So Alice sends Bob a message. So let us see how this actually happens. So I've been talking about hash algorithms. So Let us see this with the help of an example. Now we have Alice, and here we have Bob. Now, in the previous example, we saw that Alice was able to modify the data that was being sent by, like Eve was able to modify the data that was being sent by Alice. So let us see with the help of an example how we can prevent that. So we are saying that Alice sends a message to Bob. So suppose the message was M. She encrypts the message M. Now there is a technique or like encryption like algorithm which is known as the hash function. So what hash functions do is, so suppose the message here is M, and this message can be of any length. It can be of 256 bit, 512, 1024 bytes, any length of message. So what you do is you pass it through a hash function. So we are passing it through a hash function, and we call this hash function H. And finally, you receive a value, that is some value will be returned by the hash function, and this value will be called the hash value, or it is also called the message digest. So we are saying that we have a message M. This message M can be of any arbitrary length. We pass this message M through a hash function, and this hash function is a mathematical function which will convert this message into a compressed message. So the input to the hash function is a message M which is of arbitrary length, but output to a hash function is always of a fixed length. And this message digest, it is of fixed length, and it has another property. It is unique. So this message can be of any length, but when passed through a hash function, what we get here is a hash value or a message digest, and it is always in fixed length and it is unique. So let us come back here. So in order to ensure, now we were taking the example that Alice wanted to send message M to Bob, but what Bob received was M dash. Now, does Bob have any way of knowing that no, this message was not what Alice sent? Alice sent me M, but what I received is M dash. So if Bob has any way of knowing that Alice had sent him M, he will be able to know that, okay, This message M dash that I have received has not been sent by Alice, but has been modified during transmission. And this could be some kind of a network error, or it could also happen that there was some kind of eavesdropper on the network who modified or forged my data. So to ensure that the receiver is able to know whether the information provided to him or her is correct or not, let us see how that happens. So Alice sends this message M to Bob. She wants to send this message M to Bob. She encrypts this message M. Also, she will include the hash of message M. And this information is what Alice will send to Bob. So this information is transmitted to Bob. So Bob will get, now when Bob gets this message, he will get this encrypted message, and here we are saying that this message was modified by Eve. So Eve modified message M to M dash. So we had an intruder on the network who modified the message M from M dash. Now, what happens is Bob has received M dash. So what Bob will do is Bob will compute the hash of M dash. Bob will compute the hash of M dash. And when he computes the hash of M dash, he will see that hash of M which he received is not equal to the hash of M dash. Now, if this message C, the encrypted ciphertext C, had been modified, this probably will not match. And if it does match, Bob will know that the message is what? The message that he has received was sent by Alice. So we are saying here is when you send a message, you send the ciphertext and you also send the hash of the message. So for this, you use a hash function. And for this, you use an encryption algorithm plus the key. So this is what is transmitted over the network. If this encrypted text, the ciphertext has been modified, the hash of that text will not match. So this way, Bob will be able to know whether the message has been sent by Alice or not. Now, this is what it has been mentioned here. So in order to check if the message was modified or not, now Alice sends Bob the encrypted message and the hash of the message. When Bob gets the message, he will get this C, the encrypted message, and the hash of the message. He will decrypt this message and get M dash. Now, since the message was modified, we will not get M, but we will get M dash. Now, Bob will compute the hash of this M dash. hash of m is it equal to hash of m dash? No, it won't be, because the message has been modified. So if Eve has modified the message, it probably won't match. And if it does match, then Bob will assume that it is the message that Alice sent. Now, what exactly could go wrong? Now here we are taking a very simple example. Usually hash is a very big number. It is not like a 1-bit number. It is usually 64-bit, 256-bit, 512-bit. The hash message is long. But suppose the hash of some message maps either to 1 or to 0. Now we are saying that there is an equal probability of the hash mapping to either 0 or to 1. So if there is a possibility that there is only like two choices, that is, Eve has 50-50 chance of fooling Bob. Because we are saying that that hash message can either map to 0 or it can map to 1. But suppose this hash of the message X does not map to the entire range with equal probability. So if you're saying that there is a possibility that the message that has been, like the hash value of the message does not map to like either 0 or 1. Now what could happen? So what we are saying here is that we have a hash, and hash has been we have a message m whose hash has been calculated. So an important property about hash functions is that hash function is a one-way function. You can use the hash function to like get the message digest from the message, but you cannot use the message digest to get the hash function. So if Eve wants to identify which hash function has been used, it will have to make use of brute force. She cannot change the hash function because she would not know, because hash function is a one-way function. And if what will do is, if she wants to like alter the hash function also, she will have to repeatedly try to do some random modifications. And one important thing to note here is that the hash function, that is this hash function h, is tied to the message, because we are using the message to compute the hash function. So Eve can change the message. She can change the message as she wants, but she will not be able to change the hash digest, because hash digest is one way and it is tied to the message. So there is only one way to do it. You have to repeatedly try some random modifications. You have to use like hit and trial, like error method, brute force method, to identify the hash function, or the how the message has been computed from the hash function. So hash function has some properties that provides us with the security. So let us see what hash functions are. So as already mentioned, that a hash function, what it does is it maps the variable length input message to a fixed length output message. So hash functions, suppose this x is a variable length input message, we pass it through the hash function. The output, that is this y, will always be of fixed length. So if h is a 64-bit hash function, then y will always be 64-bit in length. So what we're saying is, suppose we type a message, we have a random message, and this message is, suppose this message here is so we are saying that we type a random message and we assume here that this is 250 or 10 like 56 bytes. It is not bits, we are saying this message length of this message is 1056 byte. Now we pass this message through a hash function. Now, for a moment, assume that this is a 64-bit hash function. So when you pass some message, this original message, through the hash function, you will get some output which will be like this. And this message will be of 64-bit in length. So we know that this message is called the hash value or the message digest. So if h is a 64-bit hash function, then this y, this is x and this is y. So y will always be of 64-bit in length. And there are several hash functions that are in use, and the value of y is always greater than 0, and traditionally the value that has been used is 512, but now it can also be 1048. It is the highest we have gone till now, but traditionally it has been either 512 or 264. So hash 256 is the most popular, the most commonly used hash function, and this hash 256 is what is used in the blockchains. Almost every kind of blockchain, be it the Bitcoin blockchain, the Ethereum blockchain, or the Coinbase, Ripple, Embark, all of these blockchains, they make use of hash 256. So this 256 means that whenever any data is passed through the hash function, the output hash value or the message digest will be 256-bit in length. So this is what we are trying to say here, that a hash value or a hash function, what it does is it is a mathematical function which will convert a variable length input value into an fixed length or a compressed numerical alphanumerical value. The input to the hash function is of arbitrary length, but the output is always of fixed length. And the value that is returned by a hash function is called the message digest, or we simply call it the hash values. So there are several important features of any hash function. The biggest and the most important is the hash value is of fixed length. That is, we have a fixed length output. So the hash function, what it does is it converts the data of arbitrary length into a fixed length. And this process is what we call the hashing of data. So the hash value is always much smaller than the input data. And hence, this is why hash functions are sometimes called compression functions. And since hash is a smaller representation of a larger data, this is why we are also calling the hash value as digest. And hash function with a n-bit output is referred to as the n-bit hash function. So if it gives you a 64-bit output, it is referred to as the 64-bit hash function. If it gives you a 256-bit output, it will be referred to as a 256-bit hash functions. And the most popular hash functions generate the hash values between 160 to 512 bits. So fixed length hash value or the fixed length output is one important feature of hash function. Hash functions are also one way, meaning that you can pass the message through the hash function and you'll get the hash value, but you cannot use the hash value to get the message back. It is just a one-way function and you cannot get your message back if you you cannot use the hash function to get your message back. It is just one way. And hash functions are computationally very fast. So when we go into detail about encryption algorithms, we'll study about two types of encryption, which is symmetric encryption and asymmetric encryption. So in the first example, when we are talking about the secret key, we have said that we are using a same secret key. So if you are using the same secret key at both the sender and the receiver, we call it the symmetric encryption. But if we are using different keys, then it is called asymmetric encryption. So hash functions are very fast to compute. They are so fast that they are computationally faster than the encryption, symmetric encryption also. So this is one important property, one important feature of hash function. So there is this one principle which is known as the pigeonhole principle. We'll study this principle when we study hash functions in detail. So hash function is a secure function. It is easy to compute in one direction. It is very fast to compute in one direction, but it is very difficult to compute in the other direction. It is not that you cannot do it, but it is so difficult to compute that it is almost computationally infeasible. That is, if you ever try doing getting the message back from the hash function, it is so computationally infeasible that you may waste about a lot of time and you may never get the message back. And also, hash functions have a very important property which is known as collision resistance. So we have already mentioned that hash value or the message digest is always unique. So it is very difficult to find two messages that will hash to the same value. This is known as collision resistance. I think the time is okay. We have a question here. So we'll stop here and we'll take up this question. So somebody has asked what this y greater than 0 or less than 264 means. So we are saying that this is our input. This is our input message. Now input message can be of any length. It can be of 256 bit, 256 byte, 256 megabyte, gigabyte, anything. But whenever you pass it through the hash function, you will always get a fixed length hash value or message digest. Okay. Now, there are many different types of hash functions. So we can have a 64-bit hash function. We could have a 256-bit hash function. We could have a 512-bit hash function. So this y is the hash value. That is whatever message digest you will get once you pass your message through the hash function. And y greater than 0 and less than 264 means that the value, the hash function, will always be greater than 0. And most popular used values for y are these: 64, 256, and 512. So we are saying that when you pass a message through the hash function, you get a hash value, and that the length of that hash value is determined by the hash function you're using. So if you're using a 64-bit hash function, you will get a 64-bit hash value. If you're using a 256-bit hash function, you will get a 256-bit hash value. And if you use a 512-bit hash function, you'll get a 512-bit hash value. So this y greater than 0 less than 512 means that the number of bits in the hash value will always be greater than 0 if you're passing a message, and most likely it will either be 64 or 256 or 512 depending upon the hash function that you're using. So I think we'll stop here for now. If there are any more questions, we can take them up. Otherwise, you can drop your enrollment numbers in the in-call messages and we could exit the meeting.